Great. Welcome to the I'm a Future Leader webinar today. Uh, it is my great pleasure to introduce Dr. Xiaodong Ma. He got his PhD from the University of Wisconsin-Madison in 2014. He is currently a professor at the Department of Geophysics, University of Science and Technology of China, and is affiliated with the Deep Space Exploration Lab. Before returning back to China, he conducted research and teaching at Stanford University and ETH Zurich. He is interested in conducting rock mechanics fundamentals with geoengineering applications, for example, georesources, geohazards, and geostructures, through the main research theme related to crustal stress and its spatial temporal variations. He combines laboratory and field observations, physics-based models, and data analytics to tackle modern challenges of geomechanics. Dr. Ma was an ARMA Future Leader, and he received the inaugural Distinguished Service Award in 2020. So, Xiaodong, without further ado, the floor is yours.
Okay. Wei, I just lost you for 2 seconds. I think probably it's because my network. Shall I turn off my video? I'll keep the sharing on, right? So that just to minimize impact.
Sounds good.
But
Yeah,
you
I'll
can
turn off mine as
hear
well.
me clearly, right?
Yeah, I can.
Okay, I will stop my video. Okay. Thank you, everyone. So and thank you, Wei, for the introduction. So it's my pleasure to have this opportunity to give this webinar for the ARMA Future Leader Series. So the topic that I will be presenting is the determination of the crustal friction and state of stress using natural fractures in the deep boreholes. As I present the definitions and the meanings of these, specifically, I mean, the crustal friction and the state of stress will become self-evident in a few minutes. So I will also want to take this opportunity to introduce a bit more about myself, right? As we already presented, I got my PhD in 2014 in Wisconsin-Madison, and it has been a pleasure to be a ARMA member, and I've been, I have been a member since I pursue my PhD in the US. So it's been more than 12 years. So joining ARMA, this big family, I met quite a lot of interesting scholars and make a lot of friends. And it's my pleasure to keep connected with ARMA. Although after more than 12 years, I've been abroad in Europe and in the US. And now I'm back, right? Back to back to the University of Science and Technology of China. I was fortunate to be included as a member of the Future Leader in 2018, and I would like to dedicate this talk to the program, and hope that you guys will enjoy. I've been back to China since late 2022. So I'll try to speak good English. I'm losing my English since I came back bit by bit. So please correct me if I make mistakes. So since I joined the faculty of the USCC, I've started the group, started my geomechanics group with the research keywords, three keywords, basically subsurface and the stress and the sustainability. So I've been focusing on utilizing the fundamentals of geomechanics and rock physics principles to help further the exploration of deep geoscience. And also, you all know that in China, there is still a lot of infrastructure going on, right? And also the country has great needs for sustainability. So that's why I think, the application of geomechanics can be enormous in the country. So that's also the reason that I chose to came back, right? So big cities, underground developments, and conventional reservoirs and unconventionals and emergent areas like geothermal, and also developing all these um, fields also can cause geohazards like induced seismicity and so on. And my research has been focusing on the crustal stress and its spatial and temporal variations. I'm very interested in connecting geomechanics fundamentals with geoengineering applications, like georesources, broadly defining that's more than oil and gas, right? And also geohazards, like landslides and seismicity and so on. And geostructures, right? That could be tunnels, mines, and a lot of subsurface buildings. So guided by the research theme of stress, all that I can describe is that it's been a stressful journey, right? Very joyful, actually, right? This is the sort of a document that I discovered last year when I led a group of students for the summer um, uh, exploration in Western China, in Yunnan. So probably some of the Chinese can read this, right? So I translated. It's a document from the earthquake agency in Yunnan province. It's a it's a document in 1982. So this is a document showing that actually quite anecdotally, my PhD advisor, Professor Betzalel Heimsen, right? You can see his initials here, right? Although it's written in Chinese. And my postdoctoral advisor, Mark Zobak, they were on the trip to Western China to measure the stress with hydraulic fracturing technique. So that's probably one of the first scientific exchange between the U.S. and China after this U.S.-China Science and Technology Agreement has been signed since 1979 between Jimmy Carter and Deng Xiaoping. So my interest in the crustal stress has been triggered by these two great advisors and continued until now. And all that I can remember is, that Bezalel used to mention that stress must be measured, right? So he's a very knowledgeable rock mechanicist, and he has been many places to measure the stress in situ. And my talk today will cover that and sort of put a question mark here. So whether or not that stress has to be measured, in situ, right? There will be probably some alternatives or some other methods that could be discovered. And my talk today will sort of try to move in that direction, but all the solutions might come from the future generations, I guess. The talk I'll be covering is based on a recent paper that we published on Rock Mechanics Bulletin, determination of the crustal friction and the state of stress in deep boreholes using hydrological indications. That's exactly the title of my talk, right? So I was fortunate to be included in this special issue, data science and geotechniques and geosciences, right? and has been selected as the cover of this issue. I quite honestly, I'm not so happy with the design of this infographics, but all that we want to communicate to the readers is that for a borehole, we will discover numerous fractures, right? And the fractures, whether or not it is hydraulically conductive, you can see the fluid flow, right? And some are sort of probably dead for any fluid transport. Whether or not these fractures are fluid and hydraulically conductive can help us to generate or to infer the state of stress in situ, maybe the stress state broadly covering the crustal rock mass that is penetrated by this borehole. So this will be the basis for my talk today. And it was also fortunate that has been covered by several scientific media. And I would also want to take this opportunity to advertise this journal, the Rock Mechanics Bulletin. And I have been on the editorial board, serving as associate editor for this journal since late 2022. And it's a flagship journal for the Chinese Society for Rock Mechanics and Rock Engineering. So if you guys are interested, please take a look and maybe can submit some of your latest work to this. So this is actually a better infographic that a designer actually helped me, and I quite like it. So basically, this is communicating the information that I want to utilize today. So actually, in the Earth's upper crust, the brittle crust, we measure the stress, right? Or we infer the stress from a lot of geological indicators, such as focal mechanisms, right? Earthquakes, we can detect and infer the stress, or magmatic liking, right? Active volcanic activities, or fast shear velocity based on teleseismic or other information. And we can also utilize the boreholes or the cores extracted from these boreholes to infer the stress, right? Either by active hydraulic fracturing measurements or overcoring, or the core-based measurements. For example, measuring the deformation of the cores, and or utilize the observations through borehole televiewers to examine the borehole failures, such as drilling-induced tensile fractures or borehole breakouts, right? So actually putting all these different sources of stress onto a database or a map that people usually can identify the variations or the heterogeneity of the stresses as indicated by these arrows, right? They are for a region, the stress trend is, or the stress orientation is generally coherent and consistent, but you see the variations from one place to another. And some of the one of the reasons for such heterogeneity, stress heterogeneity, is the presence of the discontinuities in the crust. For example, the fractures and faults of different scales. And this figure that shows, if we have a borehole, people have, published quite a lot examining the stress orientation or stress changes surrounding the fractures. That basically means that the fractures can have an effect on the local stress changes, right? And this is actually related to what I want to present today, right? The slipping fracture will cause sort of the hydraulic conductivity changes to this fracture or itself, and the signal may be able to be detected by some sort of probe. So that's the basis. I will come back to this topic in a few minutes. So before that, I would like to, reiterate this is sort of the brittle crust generally is at a state of frictional equilibrium. In situ stress that I want to communicate is that it relaxes primarily through frictional faulting, either seismic or aseismic. May or may not always correspond to the earthquakes. So this is a diagram that is modified from Zoback and Tungman in 2001 in tectonophysics. So basic idea is that due to the upper brittle crust, right, due to the ongoing tectonic loading, it can produce a lot of faulting for the past geologic time, right? Since the plate driving forces is continuing, right, due to the ongoing mantle convection and mid-ocean ridge pushing, right? So the deformation or the faulting in the brittle crust will be ongoing, and it can produce, or it has produced a lot of faults and fractures in different orientations and different scales, different sizes, and will keep failing. That will push the crust into this so-called frictional equilibrium. Basically, the in situ stress, if we use the shear stress, maximum shear stress that is present in the Earth's crust, it cannot exceed its crustal strength, basically the frictional resistance, the frictional coefficient times the normal stress applied on the fracture or the fault. So this is sort of dictated by the cooling failure, frictional failure criteria, right? The shear stress cannot exceed the frictional resistance. We can actually illustrate this frictional equilibrium concept with very simple modeling, right? So assuming from the beginning, we have a Mohr circle, right, defined by the minimum and the maximum stress, it already exceeds the frictional envelope, right? So that quite a number of fractures will become critical and start to slip, and it will cause the stress relaxation, right? Then the differential stress or the shear stress will drop. And if there are still fractures that are above the frictional envelope, then the faulting or the frictional sliding will continue, and until the end that this stress state is bounded or become tangential to the frictional envelope. So this is a process that we modeled that utilize a uniform friction coefficient. Basically, all the fractures, all the faults have a uniform frictional property, meaning that the frictional coefficient is always equal to 0.6, right? And this dynamic process of stress relaxation and faulting is basically what we denoted as frictional equilibrium. So why putting the frictional coefficient as 0.6, right? It's actually derived from laboratory experiments, right? So this is the classic paper by Byerly, published in 1978, right? The so-called Byerly's law is sort of this compilation of a lot of shear experiments on different rocks, right? From crystalline rocks to sedimentary rocks and to some other rock types that the basic trend is that this mu equals 0.6 can accidentally describe the frictional property of all of these rocks to a good extent, right? And later, papers, for example, by Brace and Kolstad, limits on lithospheric stress imposed by laboratory experiments, right? So this mu equals 0.6 has been utilized quite a bit, although it is derived from laboratory experiments, but has been used quite empirically as a decision boundary, right, to evaluate whether or not a fracture or fault can slip, right, to overcome the frictional strengths. So since then, quite a lot of field observations has shown that, the combination of Coulomb frictional failure criterion, right, very simple form, either in shear stress, normal stress, or in terms of principal stresses, right? It works quite well if we use this laboratory-derived frictional coefficient, right? It's around 0.6, right? So this figure is also from Zomack and Tongant, compiles 4 great data sets, right, from deep boreholes, from Nevada test site, right, and Long Valley Caldera, and Cajon Pass, which is only a few kilometers of San Andreas Fault, and the KTB borehole in Germany, right, which is sort of probably the deepest scientific borehole that has very good documentation, right? It penetrated until a depth of nearly 9 kilometers, right? So basically, with the field measurements of the stress and the identification of the fractures in these boreholes, one can calculate the shear stress and the normal stress, effective normal stress on these fractures. And you can see that nearly all of these fractures are sort of bounded by this envelope, which is dictated by mu equals to 0.6, right? Of course, there are some scatters, right? This is the heterogeneity that I would call. And this figure actually contains more information. I'll come back to this. But the point that I want to make now is, why this frictional coefficient mu equals to 0.6 is so useful. The natural system, like, the Earth's crust, this variability and uncertainty has to be considered, right? A simple example is that the frictional coefficient varies with the mineral content, right? Clay plus organic matter in some of the shaly rocks, right? So basically, combining a few studies, you can see the frictional coefficient that will drop as the clay content increases, right? That is an example of the frictional coefficient variability, right? Should have some spatial or even temporal variations, right? Even for as a simple rock, right? Wesley granite is what Byerly uses, and also a lot of rock mechanicists, they tested in the lab, right? This is basically considered as the superstar rock, right? It's very homogeneous, and people use it a lot in the lab, right? Even for the same rock, right? If we extract the cores, right, and you perform the experiments, you can see actually it's not always falling on mu equals to 0.6. Actually, it has some distribution, right? So this natural system variability, shall we consider it in our application, right? So the other point is whether or not the laboratory scale characterization is actually representative of the crustal scale friction or strengths, right? Usually in the lab, small samples are in the order of a few centimeters, right? This is a standard core. It's 1 inch in diameter and 2 inch in this height, right? So as you can see, this is a figure that I extracted from Mark's paper, right? This is a drilling-induced tensile fracture observed from the electrical image log, right? This little hole is representing a side core that compared to the fractures and the formation, it is actually very, very small. And letting alone the crustal scale rock mass, right? This is in the order of kilometers, right? Whether or not the natural system variability and uncertainty and the scale is considered in our application of the frictional coefficient in many of the in-situ stress estimation or the fracture stability analysis, right? So coming back to this figure, the more information is that Zoback and Townend actually differentiate the fluid bearing or hydraulically conductive fractures from the non-conductive fractures. You know, the conductive fractures, they have used a bigger marker, right? You can see for different colors, the bigger marker compared to the little finer dots, right? That's the conductive fractures. Usually it's sort of close to this frictional line of mu equals to 0.6, although there are quite some, scatter. But the majority of the non-conductive fractures, non-hydraulically conductive fractures are, scattered all around, all across this space, right? So whether or not the hydraulic conductivity is a good indicator of the actual stress state of these fractures or faults, that's a very good question, right? So it's basically based on the observation, right? The borehole, you can run the televiewer, you can observe the fractures of different orientations, right? And I think this is a work from the early days from Takatoshi Ito, right? He's currently at Tohoku University, right? This is the application of the KTB wellbore. The identification of hydraulically conductive fractures from the borehole temperature anomalies, right? If you screen the temperature variations, right? One can set up a threshold. If it is above some certain degrees, then if it is close to a fracture, right? People will associate this fracture as a hydraulic conductive one, right? This is based on the idea that if the fracture is, close to the frictional line, it might have a higher probability of slipping in recent or geologic recent time, right? And the shear slip will cause this dilation, and that will cause a higher hydraulic aperture. Therefore, the hydraulic conductivity will become measurable. And therefore, for the borehole, if it has the hydraulic communication, the temperature might have some anomaly surrounding these fractures. So this is a basic model for the association of hydraulic conductivity with the actual stress state of these fractures, right? So this idea, right, fracture shear slip and the hydraulic conductivity idea has been explored for quite some years, right? From the early papers to recent papers, right? People are interested in this kind of relationship. And actually, this is sort of our work that we still want to utilize these four great data sets, and we break it down, for each individual wellbore, and we would like to further explore the relationship between the hydraulic conductivity and the shear slip criticality, right? Basically, the hydraulic conductivity serves as a proxy for the stress state or the stress criticality of these fractures. So basically, Zoback and Townend utilize the measured stress states, right? All these boreholes feature in situ stress measurements. Therefore, knowing the stress magnitudes and orientations can allow one to calculate the shear stress and normal stress of all these different fractures. So hydraulically conductive fractures is colored red, right? And the non-conductive fractures are colored gray. As you can see across these four data sets, the separation is very clear. But as you can see, in some boreholes, still have quite some scatter or uncertainty. But just by arbitrarily use this empirical decision boundary of mu equals to 0.6, we can separate these two data sets quite well, right? So that comes to our hypothesis. So whether or not that we can purely use the hydraulic signature or hydraulic indicators of these fractures to infer the state of stress for these boreholes or for the crustal stress, crustal rock mass that is sampled by these deep boreholes, right? In the absence of any dedicated stress characterization. It's, for example, overcoring or hydraulic fracturing, because all of these stress measurement techniques is quite time consuming and may have risks of losing the tools in the borehole or some other consequences. So we boiled it down to the four unknowns, right? The in-situ stress orientation, which can be described by the three Euler angles, A, B, C, and the relative magnitude, because if we want to infer the stress state for each borehole, right? The borehole has the variations in terms of depth, right? If we want to normalize that, we have to consider the relative magnitude, which is the phi between the differences between sigma 2 minus sigma 1, sigma 3 over sigma 1 minus sigma 3, right? So this is actually the output for the earthquake focal mechanism stress inversions. So what we defined also is that the crustal stress or the frictional coefficient that could serve as a byproduct from our study here. So the basic idea is that we will basically use a binary classification, and same as what Zoback and Townend did, right? We will classify the fractures in the deep borehole into hydraulically conductive and non-conductive. As you can see, right? We will use image log to inspect, to identify fractures of all sorts of orientations. And we can actually do a search, right? We can, arbitrarily define a stress state with the initial A, B, and C, the orientation and stress relative magnitude, right? Based on this, we can calculate the slip tendency, or actually is the shear stress over the normal stress, right? Then we can, plot this onto the shear stress versus normal stress space, and we can see whether or not the hydraulically conductive fractures are nicely separated from the non-conductive ones. Of course, for the initial guesses, this is apparently not the case. But we can reorder our search, basically assigning other values of stresses, right? Then over the iterations, we can at least achieve a stress state that will best separate the two groups, and the maximum probability that will allow us to relate the hydraulic conductive fractures to the critically stressed fractures. And based on the finalized stress state, we can also get this byproduct, which is the logistic decision boundary between the two groups of the fractures. So this is an example that is applied to the Cajon Pass deep borehole, deep scientific borehole. As you can see, we are using a series of lower hemisphere stereo nets to indicate the stress orientation. So the beginning of the search, right? We actually spreading the seeds for different stress state on the space, right? So as you can see, we will refine our search. We will reject some of the unlike stress states and narrow our search bit by bit. As you can see, through the iterations, our stress state actually indicated by the increased maximum of likelihood relating the hydraulic conductivity and stress criticality. Actually, in this arriving at iteration 6, we've already have very converged stress state. And for comparison, the measured stress, either by the combination of hydraulic fraction and the identification of borehole breakouts, these methods have yielded very reliable stress states for these deep boreholes. So comparing our search and the measured stress state, actually they match quite well. So this stereo net is basically summarizing all the iterations from 1 to 12. As you can see, the color becomes hotter and the more converged stress state. And actually the whole the process is quite efficient, right? This is a compilation of all the 4 boreholes, right? Cajon Pass, Long Valley, and Nevada Test Site, and KTB borehole. The Euler angle for ABC, and the stress ratio, right? That is describing the relative stress magnitude for the stresses, right? So for reference, the dashed lines are the measured stress states, and through the iterations, right, from step 1 to usually not more than 20 steps, we usually reaching very stable stress states that matches the measured stress state quite well. But for some stress ratios, it could be quite off, right? For KTB and for the Long Valley Caldera deep borehole. But whether or not this measured stress state is really reflecting the in situ stress condition or actually our searched stress state, which is actually reflecting the whole borehole length, maybe it's more representative, right? I think to find out some further work must be conducted. And coming back to this plot, right, that we utilized before, and comparing to the empirical decision boundary from Byerly's law, right, mu equals 0.6, we also reached the so-called logistic decision boundary, right, for Cajon Pass, it's quite close to 0.6, right? And also for the other boreholes, they are actually sort of supporting the empirical decision boundary that has been proposed by Byerly, right? So now we see this a good agreement and from totally different approaches for the data sets that we sort of find more support purely based on this data-oriented approach, the support for the use of mu equals to 0.6 and the support for relating the fracture hydraulic conductivity with the stress criticality. There are some ongoing work that we still try to explore, right? Currently, we are exploring the critical borehole length that is necessary for a reasonable stress inversion, right? Basically, we're speculating how long a borehole section, right, and the fractures therein could be sufficient for a stable inversion result, right? Basically, if we can utilize only a fraction of the total fractures identified in the borehole, our method will be more applicable, right, to different scenarios, right? As you can see, we're for each of the borehole, each of the data set, we're experimenting different interval lengths. Basically, we have a sliding window of the length of from 50 meters to over 1,000 meters, screening across the whole borehole and locking the fractures therein to do a partial immersion, right? Based on these partial data set, as you can see, once the fracture or the borehole interval length exceeding several hundreds of meters, our inversion become quite reasonable. So this is sort of also give us some positive feedback, right? If we have a much shorter borehole compared to these four deep scientific boreholes, maybe this inversion method can still be useful. So we are also explore the data uncertainty or error, right? As you first look at these four data sets, and you can see some of the hydraulic conductive fractures can be well below the frictional envelope, right? Whether or not these are wrong data recording, or actually these fractures are in fact hydraulically conductive, that we don't know. But we actually want to see or check whether the data uncertainty may have an impact on our inversion process. The basic idea is, as you can see, for a synthetic data set, right? We can have the fractures all across the space, right? The hydraulic conductive fractures colored blue, and non-conductive fractures are colored gray. You can actually assign, a certain number of fractures that could be, well above the frictional line, but can be classified as non-conductive, or the other way around, right? So this actually reflects the possible uncertainty or the data contamination in the input data. So actually we are running this algorithm that we assume that it might not be a binary classification, right? As soon as the fractures and its stress state is close to the frictional line, right? The closer to the deterministic frictional line, the higher the probability it will be classified as hydraulically conductive. So comparing to the previous binary classification, 0 or 1, right? Non-conductive to conductive. Now we can assign this slip probability so that we can further explore, the nonlinear inversion process. So this work is actually ongoing, but some preliminary results is that if the data uncertainty or error or contamination is within some critical threshold, our inversion still works. So we can also explore the data diversity, right? Data diversity means that the fracture, its orientation or conductivity should be able to cover a wide range as opposed to the very narrow ranged values, which is not good for our inversion. Our inversion is best based on the evenly distributed fractures of different orientations, basically different strikes and dips, and the balance between the hydraulically conductive fractures with the non-conductive fractures. So this is a synthetic case that we explore, right? We actually in the space, we assign the fractures of different orientations, and we take 4 groups to sample the fractures differently, right? Either only within the limited range of strike and dip, or very narrow range of strike and dip, right? As you can see, the color of the group A, B, C, D actually corresponds to the presence of these fracture groups. As you can see, for group A and group B, the inversion result can still be very stable, and we can still reach reasonable inversion results that corresponds to the measurements. But for group C and D, as you can see, they only sample very narrow ranges of orientations of fractures. The search for stress or the stress inversion becomes unreasonable, and we basically cannot reach a stress state that will satisfy our criteria. So actually, we are also wondering whether this method can be directly applied to the boreholes and to be used to directly infer the stress magnitudes, the stress absolute magnitudes, instead of the stress relative magnitudes. So this is a case that we're sort of limited by the data sets that we can have, because these deep boreholes simultaneously with the identification of fractures and the stress measurements and the hydraulic conductivity of these fractures are very rare, right? KDB is sort of the best data set that we can have, right? This is early paper that the KDB borehole have reached or have led us to the understanding of the upper crustal strengths, right? Inferred from stress measurements, combination of borehole failures and dedicated hydraulic fracturing and other type of stress measurement techniques, right? That is very fundamental to our understanding of the crustal stress state. So we still utilize the old data, and this is our basically KDB case study. First, we focus on the stress orientation, right? As I presented in earlier slides, we can basically reach the stress orientation very stably through only a few iterations. As you can see, the inverted stress orientation is actually very close to the results from the breakouts and tensile fractures from both the caliper-based breakouts and borehole televiewer generated breakouts. These are for the KDB pilot borehole and the main borehole, right? The pilot borehole has some issues of highly foliated rocks. Therefore, the results are not very reliable. But for the main borehole, right, as you can see, the compilation of different methods that is actually very close to our search. And of course, if we filter the variations with finer degrees, right, and we can sort of reach a very reasonable stress state. Basically, the orientation can be an indicator of the whole kilometer scale of rock mass. For the magnitude, right, I've showed earlier, the iterations can lead us to the phi value, right, which is very close to the measurements. And imagine that if we don't use these integrated methods, but we only use our inversion technique, if we know the vertical stress, right, based on the density, for sure, we will know the absolute magnitudes. And if we can utilize the search or the inverted stress ratio, that it can help us to reach the magnitudes of the minimum horizontal stress and the maximum horizontal stress. So this work is still ongoing, and I think maybe we will be able to report that in future meetings. And so with all the information that I put, basically I want to use this presentation to call for some nice ideas for next generation of stress characterization. So basically, I've shown abundant wellbore data in form of fractures and the fracture conductivity as one of the proxies for the stress indicators, right? If we can collect enough number of these stress indicators, we can do this data processing. It will allow us to do the stress inversion, and it will form a stress database. Imagine we have a number of boreholes that are coming in to be drilled, to be logged, and to be identified and to be processed. We can sort of build this sort of collaborative data platform that we can utilize probably different proxies for stress and to be the input for our stress inversion and to keep building up the stress database. And I'm really satisfied by reducing the stress absolute magnitude into the Euler angles and the phi value, because these are the values that the geophysicists, especially seismologists, they talk about, right? They use focal mechanism inversions and to have the stress described in these four parameters, right? This is good for the stress data standardization. And if we can, promote the data availability and synergy, right, we can probably better connect the geomechanical and geological and geophysical communities. So for some future work, as alluded to before, right, we need more data, more such data, and more elaborated data-oriented studies, right? Some quick ideas that I could propose, right? We can probably utilize other stress indicators other than the fracture conductivity for the stress inversion. Could be some indicators or proxies that are easier to be collected. We can also, invert the stress while the drilling takes place, right? Now we have the logging while drilling, we can in real time to collect the information of these structures like fractures and do a real-time stress inversion before the borehole is finished for drilling and for logging. So for a combination of multiple boreholes in a region for inversion, right? This method is not restricted to one borehole, right? Several closely spaced boreholes and the fractures therein can be all combined for a robust stress inversion. So basically, this is a takeaway that I would like to communicate, right? Understanding the cross-slope stress or its strengths or the friction heterogeneity from simple theory, right? Basically, the relationship between stress and the fracture and its fluid flow property through abundant and diverse data, right? Now we're in this era of data science that the geomechanics community can probably utilize more of the data input for better studies. So I'm reaching the end of my presentation, right? I would like to do a little advertisement for our work. I noticed that my previous PhD student, Kai Broker, is also in the audience. And actually, he presented our work on the Pedretto Underground Lab, geomechanics studies, all right, in last year's ARMA. And he also won the Best Paper Award. And I'm sure he will be in Golden in a few weeks. And there will be another paper coming. And if some of you are attending the conference, please make sure to check our work. So that's the end of my presentation. You know, it's quite late in China, so I managed to stay alert. But if I make something wrong, please let me know. So thank you all. I'll be happy to take any questions.
Thank you, Xiaodong. It's a very interesting talk. Very good work on the stress measurement and fracture slippage. So I think we have maybe time for a couple questions. I know it's very late in China; it's midnight. So, so thanks again for staying with us for so late.
Yeah.
Anyone has any questions?
I can start.
Sure.
So I know that mining people have been working on using various computer vision methods to measure apertures and automatically detect fractures in these borehole logs. So I'm wondering if it's possible to extend your concept of taking just a binary conductive, non-conductive, which I assume is some kind of sort of whether it's open or not, to actually taking the aperture as some sort of probability distribution for whether it's been activated or not, whether that would fit into this framework or not.
Yeah, I mean, as I mentioned, there could be other proxies, right, for these fracture properties. Aperture could be one of them, right? If it is easy to be measured, right? You know, usually I've seen people try to relate this, right? They take the image log and the fracture apparent aperture, sort of have some relationship with the stress state, right? With the fracture orientation. So this could be, you know, worth some, you know, further look. Yeah.
Okay, thanks.
Please, Ma, I have also just a question. This is Jean-Luc Mutombo, talking from DRC, Congo. I wanted just to find out if in your study you also considered like sort of like the joint surface characterization, like smoothness or roughness and also slang. What's the way it is going?
Slip and slide?
Slip and slide. Yes. Yeah, sure.
Yeah, Sure. Yeah. That's a good point. Yeah. These fractures, I think the slipping fractures or the critically stressed fractures might have some, signs of, slip events either in the past or in recent geologic time, right? And actually, this piece of work is restricted to the borehole fractures and the fractures identified with image logs, right? These boreholes might not have the extracted cores. So to inspect the slicken slides or the joint surfaces or the roughness, one have to look at the cores, right? So I think as also this might be connected to Bing's question, right? Either the fracture aperture or the roughness, right? Basically, the morphology, of these fracture surfaces might have some connection with the stress state and the hydraulic conductivity, right? These can totally open up other proxies, right? But the only reservation is that the logging is difficult, but it's still much easier than the coring, right? So inspecting the cores will take more time, right? So that's my short answer, right? Thanks.
I see
Okay,
Herb has his hands on, so please go ahead.
Okay, thank you so much. I've heard. Maybe just the last one I wanted to know the diameter of this borehole.
The diameters of these boreholes. Have I unfortunately I don't know, right? But I think these are well documented scientific boreholes that you might be able to find in the literature. I'm sure these are, boreholes with bigger diameters, so that different logging tools and the instruments can be placed in there.
Okay, thank you so much. I give the words to other colleagues to ask also a question. Maybe I'll come later if I have one. Sure.
Mm-hmm. Yeah, you can also contact me anytime by email. Yeah.
Sure, sure.
Great, please go ahead, Herb.
Hi, Xiaodong. This is very creative and very innovative. The question I have is whether or not you were able to compare your inversion results with any of the classical breakdown pressure equations for the maximum principal stress.
Mm-hmm. That's a good point, Herb. So far, we have been focusing on the relative magnitude and stress orientation. So for this KDB case study that we're trying to invert the absolute magnitude. So in that, we will be able to go back to the depths of maybe hydraulic fraction measurement depths, right? Then the breakdown pressure and all that could be compared. So this is a good point that we will certainly look at it. Yeah.
Great, thanks.
Thank you, Herb.
Please go ahead, Masoud.
Hello, thank you so much. Can you hear me properly?
Yeah.
Awesome. Thank you so much for your presentation. It was really enjoyable. So I have a question with regards to the orientation of the fractures as well as its correlation with B values, the relative stress ratio. So I was wondering if you have studied that one, because in the toxic mine coordinates, the information about the orientation of the fracture is lost. So I was wondering if you have played with, plotting, for example, the orientation of the fractures versus versus the stress ratio to see if there's any correlation there.
Mm-hmm. Okay, we actually haven't tried that. I had some difficulties of getting your message. Maybe
I'm sorry.
that is a bit breaking up. But I see your point is probably related to the stress ratio and its relationship with the fracture orientation, whether there
Yes,
are internal
yes,
trends that could be identified, right?
yes, yes.
Yeah. We will probably take a look at that. Yeah. It's a good point.
Thank you.
Yeah. Thank you, Masu. Yeah.
All right. We have any other questions? If not, I think thank you very much again, Xiaodong, for the very nice presentation. And we hope to see your future work soon. Thanks.
Oh, thank you for you guys listening, right? That will wrap up my week, right? It's a Friday night. Yeah. Okay.
That's great.
Yeah. Thank you, Gent.
Thank you so much. Bye.